pretty much every civilization sooner or later reaches the stage where people need to do calculations with, let's say, somewhat unfriendly numbers. Taxes, astronomy, perhaps astrology, later on banking, early engineering. And calculations have always been done by hand, which is okay if your numbers are small, and perhaps then you can also use some aids like abacus. But if you're doing calculations with large numbers, this can get problematic, especially if you are using Roman numerals, which is what we have been using here in Europe for over 1,000 years. Fortunately, in the early 13th century, we learned from Muslim scientists about the decadic system, which actually originated in India, and that was a big help. But it wasn't as big a help as we would like to. Let me show you something. Imagine two numbers. Each of them has 8 digits. And I don't want to put some concrete numbers, so I will put slots. 8 slots. That's why I chose 8, because I can make easily 8 slots. And in each slot there is a digit. And here is the second number. And again, drawing 8 slots is actually simple using bisection. Okay, now let's say that we want to add these two numbers. How much work does it take? Addition. Well, we know how to do it. We take the rightmost digits and we add them. Write the answer here. That was easy. One mental addition, one operation. Then we do the same for the 10th digits. That's the second operation, and you can imagine how this goes. So by the time we get to the end, we made 8 mental operations. Now, you have done some addition in your life before, and you say, okay, wait a second, sometimes you have to work more, because there can be carryover ones. 8 plus 7 is 15. 5, 1 carryover. That's true. If you got extremely unlucky, you have lots of carryovers, and you get 15 operations. But that's the most pessimistic case. So this is the optimistic case, pessimistic case. You will see soon it doesn't really matter. Because my next question is multiplication. So how many mental operations you have to do? Well, how do we multiply? We take the last digit of the second number, multiply with the last digit of the first number, put the answer here. Then the second last, and so on. You know how it goes. But after you use the last digit of the second number like that, you pass to the second last digit, and again you do multiplications, and you write them in a shifted way. Like that. So essentially what we do, for each digit in the second number, we have to pair with all digits from the first number. How many pairings can we do? 8 by 8 is 64 multiplications that we have to perform in our heads. 64. I'm not going to write it yet, because we write these answers, these intermediate answers here in such a strange shape, and the last one will be somewhere here. And then we have to add these intermediate stages in columns. So in the last column, there is no addition happening. That's okay. Here, we have 2 rows or 2 lines, so it means 1 addition. Here, we need 2 additions. 3 additions. You can see how it goes. The pattern reaches this column, where we can have all 8 rows, or we do have all 8 rows overlapping. That's 7 additions. And then it goes down to 6, 5, 4, 3. You can figure it out. How many additions altogether? And when you do it, you get something like 49. Plus 64 is more than 110. I don't need to be precise, because the message is already clear. And that was the extremely optimistic case, because I didn't have any carryovers in my calculations. If we get less lucky, we could have like 7 by 8 is 56. I'm writing 6, remembering 5, and so on. We can carry over here. This number can be longer. And then we have 2 columns with 7 additions, not just 1, and so on. So this can skyrocket. You can easily have, let's say, 180 operations that you have to do in your head when you're multiplying 2 numbers, 2 8-digit numbers. So when you look at these 2 guys, you can see that it really doesn't matter whether you're optimist or pessimist. The difference is so large. And that's exactly what our forefathers noticed. Addition is nice. Multiplication, beastly. Okay? So you want to avoid multiplication. Can you ignore it? Can you just stop multiplying? Well, not quite. Multiplication is useful. So if you cannot avoid it, could you perhaps sidestep it somehow? That was a good question. 13th century, a few hundred years later, 1614. I actually don't remember it. I just looked it up before the lecture. So 1614, Guy Napier, who is causing me trouble because I keep reading it as a French name anyway. This English guy, Napier, or Scott, whatever, British guy, came up with a very strange idea. He said, okay, somebody gives you a number, and you are supposed to do some calculations with this number. But instead of working with this number, you work with a different number. So numbers are changed into other numbers. This is actually a mapping from the modern point of view, mapping that we call T. And what he really did, he invented logarithms, logarithmic mapping. What was the point? Well, he argued like that. Logarithm changes multiplication into addition. And again, he used different point of view, but in our language of transformations, we are arguing in this way. We have positive numbers, which are mapped by logarithm to real numbers. And it's a bijection, it's one-to-one correspondence, it's beautiful. Now, in this original world, we have multiplication, that we don't like, and this is mapped into addition. That's the whole point. Is that really true? Well, we have a formula over here telling us what to check. So we take two positive numbers, and first we do the operation, so we multiply them, and then we apply our mapping. And hopefully, it will be the same as going the other way around. So first we map those two numbers to the other side, logarithm x, so we send it over, and we send y, and then we add them. In other words, we connect them using this operation. So that's the equality which hopefully is true. Is that true? Well, of course it is true. It's one of those elementary identities that we memorized in high school. You know, they forced us to memorize it, and they, gave us those problems where we had to use it to simplify expressions. That was so boring. But now we can see that it's actually useful because it changes one operation into another. So here is how it works. Somebody gives you two numbers, and they want you to multiply them. So you don't want to do that. You change them into logarithms. You add these two to get a new number, and then you use the inverse action, inverse transformation, to get x by y. We just avoided multiplication, which was the point of this exercise. But when you think about it, you say, oh, wait a second. Okay, we avoided multiplication in this picture, but we have to do logarithms by hand. Isn't it even worse than multiplication? And the answer is, yeah, considerably. So where's the point of this whole business if we cannot do logarithms by hand easily? And the answer is, well, we outsource it. We let somebody else do the work for us. Because, and that's the beauty, we just need to figure out logarithms for popular numbers. And once somebody does it for us, we can reuse it, recycle it. Which brings me to another name, Briggs, who was at least as important as Napier. First of all, Briggs argued that the original logarithms of Napier had a base which wasn't exactly practical, but if we used logarithms of base 10, then it will be much, much better, and he was right, of course. And everybody saw it immediately that logarithms based 10 are the way to go. So in calculus, we work with natural logarithm because it has nice properties from the theoretical point of view. But all practical people, engineers, practical scientists, in banking, everywhere, they work with decadic logarithm. And by the way, once we know that it's a decadic logarithm, we know how to go backwards. This inverse mapping actually takes a number and uses it as a power or as an exponent with power base 10. Okay, so now the situation is clear mathematically. We know what we are doing. This is a decadic logarithm. This guy was responsible for it, and not only that, he also published in 1617 a book of logarithms. This is called Log Tables. It was a book. It wasn't all that thick, actually, where on every page you will find a number and its logarithm. A number and its logarithm. And he offered numbers between 1 and 1,000. And those logarithms were calculated with precision 14 digits. And of course, it was done by hand. So you can imagine how much work this Briggs guy had to do. And not only that, all these calculations had to be rechecked. They had to be done several times over because you don't want to make a mistake. So that was a monumental work. And early 17th century, we already had the printing press. So once the guy did the tables, they could be just printed and distributed in huge numbers. So everybody could suddenly do the calculation like here easily. Later on, a few years later, he published a really thick book with logarithms for 30,000 numbers. Wow. Amazing. Let me show how this works. Let's say 2.37 by 1.74. That sounds like an interesting question. Now, I happen to have just one page of logarithms on me. Let me see. And this page is slightly more complicated compared to the early one that I have been suggesting here. But let me sort of show you how this works, and you will see that it's not all that difficult. There are a few things one has to remember. And the first thing one has to remember is that in those charts, to save room, they are not printing decimal dots. I want to find 2.3 at the start, but instead I'm going to go for 23. So do I see 23? And the answer is yes. I can see 23 in the left column over here. Perhaps can I somehow show it? Yes. This is the row that I'm interested in. So this is the row which has 23 on the left. And now there are 10 columns, which is an interesting coincidence because there are 10 possible digits coming up in the third position. I'm interested in 7, so I look at the column which has 7 in the heading. It's this column. So in the row marked 23, I look at the column marked 7, and I can see the logarithm of 2.37. It's 03747, 3747. So that's the decadec logarithm of this number. Now I do the same thing for the second number, 1.74. So I'm looking up 17, and then I'm looking up column which has 4 in the heading. 17 is over here, and the fourth column is over here, 2405. 2405. And just in case you are curious, there are those extra columns, and they serve for even more precise logarithms if you know a fourth digit. So in fact, using this one page, I can do calculations with 4-digit precision, more or less. Anyway, I have my 2 logarithms, so I'm at this stage. Now I have to add, which should be easy, 7 plus 5, okay, about 2 this early in the morning, 1 carry over, 11, 1 carry over, 6, 0 point. So I'm looking for this number in my chart, 6152, 6152, and I don't see it. Okay, so I will scroll. 6152, okay, over here. It's the last row. Okay, now it's not last anymore. It's the one which I highlighted. And it starts 41, so it will be 4.1. And the question is, what comes next? 6152, 6152, it's over here. So let me try it again. Okay. 6152 is between these two numbers, so it's between 2 and 3. So I put 2 here, and it's between 2 and 3, so it could be 25. It's 52, it's more to the left. Okay, let me make a wild guess. So that would be my guess for the outcome using log tables. And I did quite a lot of explaining here. So you imagine that if you are practiced and if you don't have to explain anything, if you are just doing the calculation, then this can be fairly quick. You just look up 2 numbers, add them, look them again, and you have the answer. Is it more efficient than multiplication by hand? I think so, even for such a simple example. And when it comes to 4, 5, 6 digits, This is revolutionary. So this is really the way people immediately started to do complicated calculations. This was a revolution in computing. And not just that, because this is not the only identity which I was forced to memorize. So I suffered a lot, and I also memorized that logarithm x over y is logarithm x minus logarithm y, which tells me that division, which is even more complicated by hand than multiplication, can be replaced by subtraction, which is reasonably easy. I can do subtraction, no problem there. How about this one? Logarithm 1 over x is minus logarithm x. Now, this is perhaps not as useful, but it shows that some operations don't have two inputs, but just one input. And the notion of transformation can be adjusted. We don't have to just worry about operations with two inputs, but we can also make a similar formula for operations with just one input. Okay? So the idea of transformation is very general, but I want to talk more about it in the next example. So let's skip it. Let's move to another useful identity. And this one is extremely useful. Logarithm square root of x is 1/2 logarithm of x. Now, when I was at elementary school, I actually learned how to do square root by hand. And it wasn't friendly. It's even worse than division. But instead, I can just divide by 2, which is a very friendly operation. So, as you can see, this logarithmic trick, this calculation using logarithmic tables, actually replaces operations which are least friendly with operations that are very friendly. So this was the basis for all the sciences and for practical calculations for a long, long time. I'll talk about it in a second. But before I get there, let me talk about another invention. Now, sometimes people have to do calculations a lot, and you would need lots of paper and copying things, and that's boring. So people were thinking, can we somehow simplify it? And already in the 1620s, there was an invention called slide rule. Essentially, people knew at least 2,000 years ago that you can do addition, I mean the ancient Greeks, that you can do the addition using two rulers. I mean everyday school ruler, marked 1, 2, 3, 4, and so on. You put against each other those two scales, and by shifting you can do addition or subtraction, depending how you use it. So I did that in grade 1 at elementary school. We had it, as a fun activity. So people knew it, and then somebody realized, okay, why don't you also change the scale on those two rulers so that it incorporates the logarithmic step? So in the end, they ended up with just two sliders with smartly chosen scales, and they did everything in one step. So you could do multiplication, you could do division easily, just by having two rulers. That was the slide rule. Now, initially, it wasn't such a big success. Some people used it, but other people preferred the tables approach, the thick book. But in the 19th century, the Industrial Revolution took off, and suddenly there were tens of thousands, or perhaps hundreds of thousands of engineers running around the globe and building amazing things. And they needed to do calculations, lots of them, and they wanted to do them fast and conveniently, and that's exactly what the slide rule did for them. So the slide rule was improved in those days in the 19th century, and it became a really great tool for scientific calculations. Every engineer had a slide rule on his desk, and many of them had one small one in the pocket, which was great. And the slide rule became the basis and the logarithms for all the scientific advances that you can think of until quite recently. I mean, when you look at those big feats of engineering like Eiffel Tower, Empire State Building, Golden Gate Bridge, the Titanic, the atomic bomb, the Manhattan Project, even the space race, the Vostok program, Soyuz program, the Gemini program, the Apollo program, even that one, this was all propelled by logarithms and by slide rule calculations, which is amazing. So for more than 300 years, this has been the backbone of scientific and technological development of our civilization. In 1969, the first man stepped on the moon. And in the early 1970s, there are astronauts still going there in Apollo spaceships. And they still were using slide rule. They had one with them on the moon, actually, in case they needed to do some quick calculations. So that was really a technology which was around quite recently. And I can even tell you one interesting date, 1976. Let me go back a little bit. If you know a little bit about the history of computing, you know that early computers have been around late 40s, early 50s. So you might say, okay, why did they carry slide rules to the moon if they had computers? Well, those computers were expensive and they were huge. That was the problem. One computer could take up several rooms. So for an ordinary engineer, it was not an option. And it wasn't an option for taking it to the moon. In 1972, Hewlett-Packard released the first scientific pocket calculator, HP35, which was good, and probably it would fly to the moon. But it wasn't okay for everyday engineer because it was much more expensive than the slide rule. In 1976, Texas Instruments started to sell TI-30, which was the first scientific calculator, which was cheaper than the slide rule. And that was the moment. This buried the slide rule as the premier tool. And of course, in school, they usually learn things a little bit later. So around 1980, when I was in grade 6, I was actually issued log tables at school, and I was taught how to use them. And we used them in our physics calculations. But a few years later, we got calculators. And, so I actually lived through this revolution. But anyway, forgetting about computers, even as recently as 1970s, logarithms and slide rule were the kings of computation, of practical computation. So this technology lasted 3.5 centuries. This is amazing. This is the background for the modern technological civilization. And it is all hidden in one very simple logarithmic transformation. Amazing story. Let me show you something before we part. Okay. Speaking of slide rule, this is a pocket slide rule which I inherited from one old engineer who retired a long time ago, and he passed this one on to me. A real leather case, because this was supposed to last for several generations. This is a slide rule. There are some slides. The middle part is sliding. You can see there are lots of scales because it can do many more things. That's the advancement, the improvements I talked about in the 19th century. Let me show you something. Okay, so what you can see is a typical slide rule. There is a working scale over here. It's actually two scales which are mirrored. So these are used for multiplication, division. And I have another working scale over here. There are two of them, and well, there are reasons for that. You will see a little bit of it later. And I'm going to use the top one to recalculate that example. So 2.37. How do I enter or input 2.37? Well, I'm going to use this accelerate slider, and in this working scale, on the top part, I will find 2.37. 2.37, somewhere around here. And now I align 1 with it in the mirrored part. So over here, okay, I put it away so that we can see it better. I think 1 here shows 2.37. Now, this is an interesting point because you can see that I'm actually not counting precisely 2.37, I'm just approximating it. So when you are working with a slide rule or with logarithms, you are resigned to the fact that you will get just approximate answers. That's one point. The second point is that unlike a calculator where you just need to know the procedure and then you get the result, here you need to know the procedure, but you also have to have skill. You shouldn't be clumsy. So students of engineering were practicing for hours before they were good enough to actually do calculations on a slide rule without too much error. I haven't been practicing for something like 40 years. So you will see approximation of working with a slide rule. So I think that this one is against 1.37, perhaps a little bit more. Well, this is hard to say because the light is reflecting in it. I think this could be 2.37. And now in this second part, in this mirrored part, I find 1.74, which is something like 1.75. This should be easy. 1.5675, 74, let's say, a little bit here. So this is what I find in this mirror part. Let me show you here. And now I go back up into the original part, and I read the answer, 4.1 something. Now, what is this something? Could it be 3 or 2? 4.1 I'll call it 3, 4.13. So here we are. The first result done using logarithmic tables. The second result using my slide rule. Which one of them is correct? Most likely none of them. But if I were to guess, I would trust the first one a little bit more. Because if you remember, 2.37 we found precisely in our log tables. So the logarithm was most likely correct. But on my slide rule, which you can see over here, there is a little mark for 2.3 and a little mark for 2.4, but we had to guess 2.37. So I would say that my slide rule is slightly less precise than the log tables that we had, but it's because it's a pocket slide rule. If I wanted better precision, I would get a larger slide rule. The standard in generic size is 8 inches, something like that. I have one at home too, but I don't carry it around because it's too long. And there are even longer slide rules. I have read about one which is something like 7 meters long. Now, that's a slide rule, but not very portable. Anyway, here is a challenge for you. Take your calculator, punch in those two numbers, look at the result and compare. I don't know. I might get lucky and perhaps I'm close. Okay. We can do also division using those two scales. So let's say I stick with the... Well, let me pass to the second one so you can see how this one also works. Let's say that I forgot how much is 6 divided by 3. So I take 6 on the top, align it with 3 on the bottom, for instance, over here. So 6 is aligned with 3, and I go down to 1, and I find that the answer is 2. 6 divided by 3 is 2. Is that right? Oh, yeah, good. Okay, how about square roots? Okay, let's say that I forget how much is square root of 9. So I find 9 over here with my auxiliary slider, and I go down into this other calculating scale, and I find that the square root of 9 is 3. Wow, that's nice. So you can do all kinds of calculations with a slide rule. Let's have a look at the last two scales that we can see over here. One of them, the second from the bottom, is marked sine, and this one allows you to calculate sines. So let's say if you want to know how much is sine of 30, you find 30 on the scale over here. And then you go up, and you see that sine of 30 is 0.5. Is that right? Yeah, that's right. Sine of 30, 0.5. In degrees, of course. So you can do tangent, you can do all kinds of stuff. And this middle slider can be also turned around, and it has also some other scales. So essentially, this little slide rule can do everything that a school calculator can do. And this is a technology which is more than 100 years old, and it has been quite recently the top-of-the-line technology for calculations. This is amazing. I'm really happy that I have this slide rule because it feels very romantic to work with it. I actually don't work with it a lot, but yeah, it feels good. So this is it for this extremely useful, but in fact quite simple transformation. This is probably the single most useful transformation in human history. So let's enjoy it, and let's move to another example.